Madison College, Building Construction for the Fire Service, Week 5. This would be the 8th problem that you'll encounter in the homework. As you can see here, there's a beam that's simply supported on a roller at point B and pinned joint at point E, and it has a series of loads pushing down on it and a couple of horizontal loads pushing to the right. So the first step to dealing with a complex picture like this is to kind of try to simplify some of the complex parts. So first thing is, this load over here is 600 pounds per foot, and it's over a distance of 5 feet. Well, 5 times 600 is like 3,000 pounds acting at a single point. And so I can strike all of these vectors. I'll just draw a line through them, and I'll draw one new vector that represents a 3,000 pound force. And if you think about where it's going to be, because this was uniformly distributed, it's going to be halfway across. So it's going to be 2.5 feet from point A. Let's see what else we could do to simplify this thing. A similar situation over here. So I've got 1,000 pounds per foot, and it's over a length of 5 feet. So I just simply multiply, and I find out that this is equivalent to a point load of 5,000 pounds. And again, it's uniformly distributed, so I can just strike all of these vectors and draw a new one in halfway over the represented length. And again, in this case, that's going to be 2.5 feet. What else do we know? Well, we can break down this 1,200 pound force into some vertical component, and it's going to be pushing down, and some rightward component. And we have to do some more calculations to get exact numbers, but this is simplifying the picture a bit. Now, for the supports B and E, let's think about B. B is a roller, and that means that if you were to try to push sideways on B, it would just simply roll along and would develop no resistance to that push. What that means is that B can only push up on the beam. B is not able to offer any resistance in the X direction. So, I mean, just by looking at this, we could say the force in the X direction at point B has to equal 0, because point B is not capable of developing any type of an X force. It is going to develop some Y force. Point E is a pinned joint, so point E is anchored. It's a pin. It's not able to develop a moment, but it's capable of developing both an upward push, and it is also capable of developing a leftward push. And the way I know that E is pointing, the anchor at point E is pointing leftward on, pushing leftward on the beam, is the fact that this 1,200 pound force here and this 900 pound force are both pushing to the right, which means that E has to be providing reaction to the left. So that's the first step. I'll pause the video here and clean this up a little bit, and then we'll proceed with the analysis. So here you can see I've simplified the drawing, and I've added the 3 equations that we need to solve for all of these types of problems. And so if you look, we're trying to find the sum of the forces in the X direction, the sum of the forces in the Y direction, and the sum of the moments about point E. And you wouldn't have to use point E. I suppose you could use point B, but I think point E is probably the simplest case. So let's think about the forces in the X direction. Well, one of them is this 900 pound force on the end, and it is to the right, so it's a positive number. So I'm going to just put a little line through that so that I know that that's that I've accounted for that, and I'm going to write that in. 900 plus what other X direction forces do we have? Well, we've got this horizontal component of this angled vector, which is 1,200 times the cosine of 37 degrees. So let's calculate that up. 37 degrees, we're in degree mode. I take the cosine and I multiply this by the hypotenuse, the length of the hypotenuse, and I find that it's about 958. And what other X forces are there? Well, the only other place that there can be an X force is there needs to be a reaction to those 2 forces over here at point E. And if you think about, if this is in static equilibrium, all of the X forces have to add to 0. So the force at point E needs to be negative, it needs to be to the left, and it needs to be equal in magnitude to the 2 forces to the right. So the remaining part of this is going to be a negative number, and it's going to be 900 plus 958 added together. And so you'll notice that the sum of all of the forces in the x direction is 0, and that by definition that's how this needs to be, otherwise this would be accelerating. Now let's think about forces in the y direction. Well, we have this 3,000 pound load over here, and we have this 1,200 times the sine of 37 degrees vertical load here. So 37 degrees, we'll take its sine, multiply by 1,200, and we find that, let's try that again. 37 degrees, take its sine, multiply by 1,200, and we see that it's 722 pounds. Now, I should be careful here in terms of direction, because both of these forces we've looked at so far are downwards. They'd get a negative sign. In fact, I could just strike this plus. Negative 3,000, negative 722. There's a negative 5,000 pound force. And then what I don't know is the force at point B in the y direction, so I'm just going to call that FB, and the force at point E in the y direction, because both of those will contribute. Now what do I know? I know that force B plus force E must cancel out all of these negative numbers, which would be 8,722 pounds. But I don't know yet how those forces are distributed between B and E. To find the answer to that, I have to calculate this moment about point E. So let's look at the moments about point E. Well, we have this 5,000 pound force that is 2.5 feet to the left of point E. So the moment here is 2.5 times 5,000, and you'll notice that this is producing a tendency to rotate counterclockwise, which is a positive moment. And it makes sense because it's a downward force, which is a negative force, and it's to the left of point E, which is a negative distance. Well, a negative number divided by a negative number, or negative number times a negative number, is a positive number. So it's going to be 2.5 times 5,000 pounds, which is going to be 12,500 pound-feet in the positive direction. Plus, what is the moment created by, well, let's look at this horizontal component here. This 1,200 times the cosine of 37 pounds, effectively this force is acting through the center of the pin. So this cosine, this horizontal component, has no contribution to the moment. The vertical part of this has that 722 pound contribution to the moment, and it's at a distance of 10 feet. So it's going to be 10 times that, so 7,220. And again, that's going to be a positive number because it's a negative number. It's a negative distance times a negative force gives us a positive number. Then there's this 3,000 pound force, and that 3,000 pound force is 2.5 feet plus 5 feet plus 5 feet plus 5 feet, so 17.5 feet. So 17.5 feet times 3,000 pounds. Oops, not 30,000 pounds. That's going to contribute 52,500 foot-pounds. Now the last component that I haven't addressed yet is what point B is doing. And if you think about all of the moments that we've created so far, they've all generated, all of these forces have generated positive moments. That's to say that they're trying to turn this beam in the counterclockwise direction, which means that B has to equal and opposite clockwise moment. So what we're going to do is we're going to sum these three moments, and that's going to tell us the moment that has to be generated by point B. So let's take a look. 12,500 plus 7,220 plus 52,500. Okay, so B needs to generate a moment that is opposite to this, that is the negative of that, so negative 72,220. Now the question is, how much force has to be present at B to generate that 72,000 pound moment? Well, this is not too tough to figure out because the moment is the force times the distance. So if you think about the moment about point E, so the moment about point E generated by force B is equal to force B times the distance to point B. Well, point B is 5 plus 5 plus 5 is 15 feet. And we know that that moment is negative 72,220 pounds. And keep in mind that, really this 15 feet is a negative distance because we're going to the left. So how do we get the force at B by itself? Well, we divide both sides by negative 15. So force B equals that number divided by 15, about 4,815 pounds upward at point B. So we know this force here. Well, if we know the force at B, then we can calculate the force at E. So let's just write this in, 4,815 pounds. Well, what do force B plus force E have to equal? They have to equal the sum of these other three forces here. So if you think about, let's add those together. $3,000 plus 722 plus 5,000. And those are all negative numbers because they're downward push. So we have this negative 8,722 pound downward push.
Because I was wrong, I knew there was something with his release form, but I couldn't call Chief Green, and I thought it was that he just...
722. Plus, we know the positive force at B is 4,815.
So I went downstairs, I'm like,
like I
said, I was going to...
Plus the force at E in the, this would be in the y direction, must sum to 0. So how do you get force E by itself? Well, we can add the two components we know. That'll give you a negative number and push it over to the other side. So 8,772 minus 4,815. The vertical component at E has to equal 3,907 pounds. So the last thing that you have to figure out, now that you've figured out both vertical reactions, is the horizontal reaction. Well, the horizontal reaction at point E is just simply going to be what it takes to counter this horizontal component of that angled vector plus this original horizontal component. So that 1,200 times the cosine of 37 was 958 pounds. Actually, we've already calculated that number here, right? The sum of the forces in the x direction. This has to be 1,858 pounds. So you can see there was nothing terribly complex about that process. It was laborious. It was a lot of steps, but the mathematics wasn't particularly challenging. Hopefully that makes it a little clearer how to solve this type of problem.